now. So the session is being recorded. We have Linda with us until almost 7. And we can work, as well. We can work through 7:15. This is the last regular meeting. The next time we meet, we'll be taking the final exam. So let's dive into then. And I did give you a video on these in-game notes, but we're going to go over it. And I want to make sure that that everyone understands what's here and things like that. Okay, so these are called end-game notes. Now, this is the scope statement for the final exam on physics. So, this is useful for you. And one of the things we might do later in the period, and Linda, I haven't thought of a good way to do this. If we were in a classroom, this would be easy to do. It might be very difficult to do in Zoom, but I don't know. If we were in a classroom, Linda, what I would do is I'll talk a little bit about all these things, but then what I would do in a classroom, I would just ask people to raise their hands if they were interested in each of these things, and I decide which one of these things we would talk about and in what order and things like that. And that would be a useful way to spend the balance of the period. I don't know if there's really a convenient or a useful way to do that.
Yeah, so there's actually a hand raise button that they can use, and I can just look at how many people are actually raising their hand.
All right, well, we'll do that then, Linda, and what you and I then will do, probably more you than me, we'll tally sort of what we have and who's interested in what and things like that, and we'll take the thing that more people are interested in. We'll do that first, and then we'll kind of work our way through. And that might not have been clear, Linda, but I'm thinking you probably understood what I was talking about.
Yeah, gotcha.
Okay, good. So maybe we'll think about doing that in a bit, but let's go through this first. Okay, so there are 11 equally weighted problems. And this is also a timed exam, and so you will have 1 hour and 10 minutes. Let's see, did I do that right? Yes, an hour and 10 minutes, 1 hour and 50 minutes to do this. So that's 110 minutes. That means on average you have 10 minutes per problem. Let's just say that. Now, so that's what we will have. And these are the short topical descriptions, and these are my topical descriptions, but I looked at the problem and I kind of said, what's here in the problem? So I'm really trying to help you. We studied many more things than this, but also this is kind of an open-ended kind of thing. And later on, when Linda and I do the poll to see what people want to talk about, that will give us a sense of priority, and we can help the most people the most in these problems. And we'll try to come up with, either we'll talk about them in kind of general, or maybe we'll try to make up a specific problem that we will do. Okay, the first topic is called dimensional analysis, and this has to do with changing units around. But there is a problem that I think is dimensional analysis, and it's one of the 11 problems. And I think it's primarily a dimensional analysis problem. The second topical area, this has part A and part B, and part A is a projectile motion kind of problem, and part B has to do with density. And those two things are kind of both in the same problem. Problem number 3 deals with Snell's law. And we talked about Snell's law last time, and we talked about the velocity components, and we talked about the index of refraction, and we did a bunch of problems and things like that. And there is a Snell's law problem on the final exam. There's an intensity problem, and the intensity problem is the one where we talked about the whispering, and it also was a problem where we talked about the the bird chirping and things like that. It had to do with attenuation and dBs and stuff. So that was an intensity problem, and there is an intensity problem. There's a problem that deals with wave motion. And you might remember that there's velocities associated with waves, there's frequency, and there's wavelength. And these are related by the fundamental equation that velocity is equal to wavelength times the frequency. There's a force in vector problem that is on the final exam. There's a Doppler effect problem. We talked about Doppler effects a bit and solved some problems with those. I'm trying to remember, I think this was the fetal heartbeat problem that we solved when we did this. There's a problem dealing with the range equation and the 13 microsecond rule. And that's another thing that we covered. There's a problem dealing with pressure. You might recall pressure has units of Pascal, which is a Newton per square meter, and it has to do with the perpendicular force. There's a conservation of energy problem, and there's a problem that deals with, and this is my characterization of it anyway, Newton's 3 laws of motion. And so anyway, those are the topical areas that we covered, and we covered all those. We did problems on all those and things like that. And now I'm going to ask you some problems on this test a week from tonight when we're going over this. Okay, so that is I guess that's good for that. And let's go to the next page. Now there's some other key elements. One thing is I have put the grace notes in your syllabus tab, and I think we'll go over those tonight, and that's at least one element of the review. And maybe what we'll do is maybe we'll do a little bit of the hand raising, and then we'll give Linda maybe an opportunity to do some tallies on that, and then we'll read through the grace notes. Or maybe I'll wait and read through some of the grace notes after Linda leaves. I haven't really decided, but again, it's important that you know what is in these grace notes. The VCM class will have their exam on 12/13 from 6 p.m., which is, so it's 1 week pretty much from right this instant, to 8:50 p.m. So you have an opportunity to stay longer if you want to. Now this is going to be a lot like the midterm exam in that there is going to be an answer sheet for you to complete, and you have to complete the answer sheet. That's going to be the primary grading instrument, but there will be an opportunity to upload PDFs of your work later if you want to. Now that's what's happening in the VCM for the most part. In the net class, what will happen is very soon, and I am not sure when the testing center opens tomorrow, but I'm going to be in very early, and I'm going to be prepared early in the day to deploy these net exams in the testing center tomorrow. Now, and I will announce this when it's there, so I can say, oh yeah, you guys can show up there at the testing center. And these things, I'm going to pick them up at the close of testing center business on 12/13. Now that might actually, in my case, be whenever they open on 12/14, because I'm going to be busy with y'all that night doing that at 12/13. And they're probably going to be closed whenever Linda and I are finished here. And Linda, you're coming to help proctor this exam, I think, and I guess I'm asking you 2 questions at once, and you're getting paid for doing this, yes?
Yes and yes.
Okay, excellent. Okay, so anyway, the net exams, though, will have the same time constraint. So whenever you do this, there will be a password that you'll be given. And once you input the password, that's when you can start reading the exam. You can't read it until you've input the password. But once you've input the password, the clock starts, and you will have an hour in, 50 minutes, which is also, let's see, 110 minutes. So you have the same thing. Check their hours means that what you want to do is make sure you know when the testing center is open, because if you go there when they're closed, it doesn't do you any good. And their hours are somewhat variable now. It used to be they were open pretty much all the time. Now, not as much. So you want to check that and plan your life there. You will be allowed to use, just like the students in the VCM, you will be allowed to use Excel or your calculators. But I need to know about accommodations as soon as possible because, and this was a horribly long and complicated story at midterm, we don't have that long to do this now. And so we've got to get this stuff done more quickly. So make sure you're following up with me if you have accommodations that we need to deal with. And some of you have, and I'm having some of those discussions right now, but probably have not had that with everybody. So anyway, those are some of my other key elements. And I guess this was the just the closing slide because I did make a video of that. Okay, so I'm going to pause now and ask if Linda has anything she wants to add or demand that I clarify or whatever, and then I'm going to recognize the students for any questions or comments that they may have. So Linda, do you have anything you want to say to the students?
So I think you're good. Just as a reminder to everyone, we will have one final GSG session right before the final. That'll be from 5 to 6 p.m. on the 13th.
Okay, so that's probably last minute questions. That's not going to be, yeah, I mean, that'll be sort of a final tune-up. Okay, so that will be good. And Linda's being, I think, gracious doing that. I don't think she has to, but I certainly hope she's getting paid for that. Okay. Let's see. Anything else, Linda?
No, I think we're good.
Okay, so now I'm throwing it open for student Q&A. And we'll do this as long as people have questions and answers. And then after this, Linda, what I probably will do, assuming that we've answered all the questions, then what we'll do is we'll go back and we'll think about doing a poll, and I will kind of turn it over to you to lead that because you said you had an idea about how people could raise their hands and stuff, and so you could do some counting. And we'll go back to the previous slide and go through and figure out which one of those people really want to talk about. Or I guess I'm going to ask you, Linda, or do you think that just going through the grace notes should be happening first?
I think going through the grace notes would probably be better, just because I feel like a lot of people are going to be a little concerned about what equations they need to memorize, what things they actually need to know. So I think going through the grace notes will give them a better idea of what they need to study up on.
Okay, so we're going to do that first and first we're going to have any student questions that are laying out there. But then we'll go through the grace notes relatively quickly, I guess. And then Linda will do and I'll try to do the poll before you leave. So at least we have a sense of what things we might want to talk about beyond that. Okay, so I'm throwing it open for student comments. I'm going to do a long count here in case people have questions, and people can either throw up questions in the comment area, or they can, and Linda will probably field those, or they can raise their hand, or they can just start talking. If two people start talking at once, I'll pick one of you. Okay, so we're throwing it open for student questions now. Okay, that's good. So now, Linda, what I think I'm going to do is I'm going to begin, and this is kind of along with your recommendation, I'm going to share my screen, and we're going to go to the application screens, and I'm going to, I need to think about how I want to do this. I think I'm going to use a different browser so I don't get screwed up on this one. And I'm going to go into Blackboard. All right, so what you should be seeing is the Edge browser, and I will go, let's see, so this will be Blackboard. I'm going to log in again to Blackboard. Okay, and doing that. And of course that didn't work, so we'll try that again. And I'm not sure why that's not working. I'm going to be very careful this time when I type that. Okay, that worked. And Linda probably will appreciate this as being a Freudian slip. My password has a word in it, and instead of typing the word that I have there, I typed a sound, which is what a lot of what we're studying here, because we're studying ultrasound. Anyway, we're going here, and I think it is in the syllabus tab is where I have the grace notes. So I'm going to the syllabus tab. And here's the syllabus tab, and I will find the grace notes. And this is where the grace notes are going to be. So you just will go here and, look at these. So here are the grace notes right here, and opening them. And like Linda said, I think what you want to do is view this as, okay, so now I know what the grace notes have in them. Okay, so this is chapter 1. And so standards, units, and unit conversions. And these unit conversions from the chapter 1 are useful. And you remember that we had to talk about things like, millimeters and kilometers and things like that. And those things certainly can come up whenever we're doing the work of unit conversion and when we're doing the physics. Okay, significant figures, we talked some about that. But the biggest thing I think we probably talked about in this chapter was vector addition. Not vector addition, but vectors in general. And you remember vector was something that had magnitude and direction. And so you were pointing in a direction. And this is really the main way that Linda and I taught you to do vectors, is what you're seeing right here. And again, this actually is what you've got. So you want to know what's here. But this tells you that the x component of A is going to be A cosine theta, and the y component of A is going to be A sine theta. The length of A is going to be the square root of A sub x squared plus A sub y squared. That's the magnitude of a vector. And the direction of the vector is going to be theta is equal to the inverse tangent of, and then we have the AY over AX, and that's the direction. And so we did a lot of problems there, and you might remember that what we did is we broke things into components. So if we had a vector A that was here, we broke it into AX and AY. We made it into right triangles, and we always dropped our perpendiculars to the x-axis to figure this out, and we did a lot of problems with that. Now, one of the key vectors that we talked about was velocity, and the average velocity is the change in location divided by the change in time, delta x over delta t. So we talked about that. We also talked about acceleration, and again, we're talking about acceleration in one dimension here. But the acceleration is also a vector quantity. It's the change in velocity divided by the change in time. So we did quite a bit with this. And then we came up with a set of equations. And this set of equations was equations, and we're in chapter 2 now. But this set of equations were equations that we really used for whenever we had constant acceleration. We used these, and so we had a whole bunch of equations. The first two come mostly from the definitions, but down here, what happens is that this equation that's called 211 is the only equation that doesn't have time in it, and that's kind of a clue for when we're going to be using that equation. We also talked about things being directly proportional to the square and inversely proportional in this chapter. And we also talked about what happens if you do this in the y direction instead of in the x direction, or whenever you just take x to be y. So this is up and down. So here we introduced and started talking about the acceleration due to gravity. And so this is what g is. That's 9.8. And you have to pick a coordinate system. Now, if you look at these carefully, you'll say these are really the same equations, except we're talking about y's instead of x's. And that's a good observation. And later on in a subsequent chapter, we learned that the x direction and the y direction are independent. You might remember the one problem where you were dropping I think you were dropping an egg on top of a physics professor's head. And that was kind of a famous example of that. And then we have relative motion too. So if a car is going 10 miles an hour from your left to the right, and another car is approaching it at 25 miles an hour, together the two cars are approaching each other at 35 miles per hour. In chapter 3, we did start talking about doing this in 2 dimensions, and realizing that the y component and the x component are coupled, but they're also independent. And so we talked about some of that. And you remember we talked about projectile motion, where something is shot at an angle, and so it goes up and then it comes down, and the maximum height occurs when the velocity is 0, when it changes from being positive to negative. And so we have those kind of pictures. And we talked about relative velocity there as well. Then we went into chapters 3 and that was chapter 3. Then we went into chapter 4. And Linda, is this playing out as being useful the way you thought it was, or is this a bad idea?
No, I think it's pretty useful. I mean, especially looking at what equations they're going to have and what variables they need to know what they mean.
Okay, so I'm going to stay the course and do this for a while longer then. Okay, so then we start talking about force. And you remember that force is F net is equal to ma. That's called Newton's second law. And so that means it's a kilogram meter per second squared. So that is what we call Newton. And that's a unit of force. And we talked about force having components, and of course it is a vector. I think I told you the story about pulling my grandson in his sled, and that's kind of what this right-hand picture could be taken to mean. And here is Newton's second law. So the net force, if you balance all the forces out together, you get m times a, and that's the acceleration. We talked about if you could take a whole bunch of vectors of people pulling, you could add the vectors together and find out the resultant, the direction and magnitude, and that's what we did. We made a big deal that there was a difference between mass, which comes in kilograms, and weight. And the difference is a factor because to get weight, you take mass times the acceleration due to gravity. And that's what this equation 4.9 is about. So the weight of an object is its mass times the acceleration due to gravity. So they're related things, but not the same thing. Newton's third law says for every action, there's an equal and opposite reaction. And we started talking about drawing free body diagrams to solve some of these problems, because then we can break things into its different forces that are acting on things. And so, for example, here, if we do a free body diagram of a man dragging a crate, the diagram shows all the forces acting on the man and only the forces acting on the man. Okay, so that's what we were doing there. And if all the forces balance out, then the net force is 0. We also talked a bit about things being on an inclined plane. You may remember these pictures where you had the angle of the inclined plane was at alpha, but if we looked at similar triangles, we can see that there's a bunch of triangles that are like that. And so we get a force which is the weight times sine of alpha, which is tending to have the crate slide down the inclined plane. But we also have that W cosine alpha is pressing down or pressing back up because onto the inclined surface. And this allowed you to answer many questions about what happens if you were looking at things on an inclined plane. And then we had some applications of Newton's law, and you'll see this is similar. We had up here, we were talking about Newton's second law, and down here we were dividing things into its components. And so we got components that would either resist the motion of something down the plane or cause it to go down, and so on. And we talked a little bit about friction, and friction opposes that. And we also talked about elastic forces. We talked about Hooke's law. And Hooke's law said if you took a spring and extended the spring, the force of the spring is K, which is the spring constant times the change in L. And so what you have is the force is equal to within elastic limits is equal to K times delta L. And this could be positive or negative depending on if you push the spring in or pull the spring out. That determines the direction of the motion caused by the spring. And that, you see, that is a force. And in the next chapter, or I think it's the next chapter, maybe it's 2 chapters from now, we'll learn about energy. And energy is force times distance. And there are other ways to get at that. But force times distance is going to be what we call work. And work would be a kilogram, or actually work would be a Newton meter, and that we called a joule. So that was units of work. And this is what happens in the elastic case. So the force to restore something disturbed from its equilibrium is going to be K delta L. Then we started talking about energy, and we talked about 2 big kinds of energy. Actually, I guess we talked about 3. We talked about kinetic energy, and we learned a formula for kinetic energy. There we're talking about work is equal to the force parallel to the displacement times the displacement. And we talked about vectors again, but we talked about kinetic energy, and kinetic energy was this one here. It is 1/2 mv squared. And so that's an energy of motion, and that's called kinetic energy. We also learned that there was a conservation of energy, that the final kinetic energy minus the initial kinetic energy is the work done on an object, or the work done in total is the change in kinetic energy. So again, the kinetic energy is 1/2 m times v squared, and this also comes in units of joules. So kinetic energy has joules, but also we talked some about potential energy. And potential energy, there were at least two flavors of this that we had. There was a thing called gravitational potential energy, which is this 710, and that says that the potential energy due to gravity is mgh. And the other kind of potential energy we can get is when we stretch or compress a distance x from the uncompressed length of a spring, in which case this potential energy, it's energy that's there waiting to be tapped, but it's not tapped yet, is equal to 1/2 k x squared. Okay, and what happens is there is a conservation of energy, and if you ignore friction or other dissipative forces, then what happens is it's purely just that. So, for example, when you lift a book up from a tabletop, you're increasing its potential energy because you're raising it higher and higher. When you let go of the book, what happens is that kinetic energy, that potential energy, and that's all of it, is changed to kinetic energy, and that's why the book makes a noise when it slaps the ground. The other kind of potential energy happens when, and this is called elastic potential energy, and this is when you have a string that is stretched or compressed x from the equilibrium. So for example, if you pressed in a distance of x, as you see here, you have stored up potential energy, and this is the elastic potential energy, is going to be 1/2 k x squared, where k is the constant of proportionality in that case. And that energy was conserved, and that means that the kinetic energy initially plus the potential energy plus any work that happens in the system, and this could be friction or something like that, is equal to the final kinetic energy plus the final potential energy. And sometimes these other forces are called non-conservative forces, and those are like friction. So anyway, and I do have a problem on the test that is called conservation of energy. So that's a good thing. And let's see. Then we started talking about power yet. And you might remember that power comes in watts, and a watt is a joule per second. So it's energy per unit time. And that's what it says here. Power is the time rate of doing work, or the rate at which energy is transferred or transformed. And so that is the change in work divided by the change in time. So that, and then we did some problems with that, but actually not a lot of problems until later. But you remember that the unit of power then was a watt, and that would be a joule per second. Then we went into chapter 11, and the biggest things we talked about in chapter 11, as far as things that you're going to be asked on the final exam, are the equation for pressure, which is pressure is equal to the force perpendicular divided by area. And the other thing that we could do here is, I guess I didn't do it, but I certainly could have. I could have invented a problem here and talked about that, and we did problems in class with that. So let's see, elasticity. We talked about simple harmonic motion, and this is kind of saying that, oh, this is the motion that is kinetic, and this is a potential energy if you're going back and forth with a spring in a linear manner. And you notice here, and this is something that you do find on your placement exams, that the energy, which is equal to 1/2 k a squared, is very close to the amplitude that we have here, and so that kind of gives you a sense of how how that is played out. And we did have equations of simple harmonic motion, and these are the sines and cosines. And I guess we talked a little bit about how some of these motions could be damped over time, get weaker and weaker. And then we started talking about mechanical waves, and mechanical waves move through the system. Actually, the molecules aren't moving with sound, but there's energy moving along, and the velocity is the square root of these two numbers. That's the tension strength, and the other one is the mass per unit length. Okay, and so what we learned is we can add these signals together and we get positive interference or negative interference. We learned that sound was a longitudinal standing wave. And we got to, in this chapter also, these are variations on the F equal, let's see, F is equal to, I'll do it the other way, V is equal to F times lambda. So anyway, you had variations on those. And then we talked about things can add constructively, making the resultant signal bigger, or they can add destructively. And we saw some examples of this. And in particular, this is where we started talking about that bird problem, and I talked about intensity. And this is another thing that I said was definitely on the test. Is intensity is equal to the power from a point source divided by the surface area of the sphere surrounding that of radius r. And you can see that as you drift out away from the point source, the intensity goes down because the area over which it's spread is bigger. And the bird problem, which is similar to a problem that I'm going to ask you on the test, was a logarithmic intensity scale. Wow, Linda, this is taking a while. We did a lot of work, Linda, I think, this term. Anyway, so this is a logarithmic intensity scale. And you might remember that this was where the dBs came in. And you remember on your, I told you that on your certification exams, they'll ask you what happens if there's if the power is reduced by 50%, what is that in dBs? And you learned that is a 3 dB change. And we did a bunch of dB problems, and we talked about these intensities. And that, I'm moving this back up one more time. That's this equation that's shown here as 1214. So that was an important equation that we had to solve, and I think you'll probably have to use an equation like that to solve the problem that I have. Now this reference intensity down here at the bottom, this I0, is the threshold of hearing. This is what human beings can hear. So this would be like a whisper. Now your ear is a magnificent instrument, and it enables you to hear things that most people can't. Well, I don't want to say most people, but this is actually a remarkably small thing. You can hear 10 to the minus 12th watts per square meter. And we call these units decibels, and we did a bunch of problems with that, including the bird problem, which was one of those famous examples that we do in this class. We also learned that when two waves of slightly different frequency exist, there's a beat frequency. And that equation ended up being, and I showed you algebraically why this was true, that the frequency of the beat was the difference between the two frequencies. Now you might think, well, why is that good, or what is that really telling me? And what's that's really telling you, at least from an ultrasound point of view, is you see if you're doing a Doppler study and you're taking the signal back, but the blood is moving, it comes back at a different frequency than what you sent, and so that beat frequency actually is the Doppler shift in the equation that we studied. So that ended up being quite important. And in fact, that leads us to the Doppler shift. And so here was the discussion we had about the Doppler equations. And this said that the frequency of the listener is equal to the velocity, that's the velocity of sound, plus the velocity of the listener divided by the velocity of sound again, plus the velocity of the listener times the frequency of the listener. This would not be hard, except you have to be concerned about, are these signs positive or negative, and you have to keep that straight. So these problems can be complicated, and we did a bunch of problems like that. And there is a problem, there is a Doppler problem on the on the final exam. So this is an important concept as well. Okay, so continuing to move on then, let's see what happened here. Oh, they just said things about the fact that you can do ultrasound, and if you and that dolphins and other insects use ultrasound waves too, and so we talked about things there, and you learned that what you can hear ranges from around 200 hertz up to 20 kilohertz. But then the frequencies that you're using in ultrasound typically range from 1 to 5 or 6 megahertz. So there's a big range there. And what you can do is you can use ultrasound waves with much higher energies to break up kidney stones or gallstones. Although that wasn't the focus of this course, we were talking just about the imaging part of it. Okay, so we talked about that. At the bottom, I do list an equation, and since you're really looking at the actual things, and this is a good equation that often is just used in ultrasound textbooks when they're talking about this, and it says that the Doppler shift is equal to twice the cosine of theta times the transducer frequency times the velocity of blood times the propagation speed. This could be negative or positive depending on if the blood's moving to you or away from you. And certainly that's the kind of problem that I'm going to ask you. Then we talked some more about density, and you might remember that there's pressure and density. I think that we're in fact, definitely there's pressure and density that we're in these on the test. And so the density is this equation 11, or is 13.1. And that says that rho, that looks like a P, but it's called a rho, is equal to the mass over volume. And then the pressure is the force perpendicular per unit area. And we talked a little bit about Pascal's law, and we did some pressure problems. And we talked a little bit about Bernoulli's equations as well, having to do with pressure. And then we got into the topic that was Snell's law. And again, this is another thing that you're supposed to know about. So we talked about index of refraction, which for light waves is given by this, but you see the same thing happens for sound waves. So that's good. And we learned that there were some things that happened. Let's see. Oh, here's a nice picture, I think. So this picture says that what we have is that the angle of incidence equals the angle of reflection, but some of it goes through. And we talked about this as has to do with the transference of energy, and it has to do with the respective indices of refraction, or the density and in the nature of the two substances. But you also saw that the transmitted energy is also bent, and these measurements were always made relative to the normal. And one of the big, I guess there were maybe three big conclusions here. Incident, reflected, and refracted rays and the normal all lie in the same plane. And that might not be obvious to anyone, but that's actually a finding here. We also learned that the angle of incidence is equal to the angle of reflection, but again, that's measured relative to the normal to the surface. And then the refraction happens according to Snell's law, which says the sine of theta A over the sine of theta B, where theta A and theta B are measured relative to that normal, is equal to the ratio of the index of refraction of B, substance B, over the index of refraction of substance A. And so that meant that this is, let's see, how do I want to say that? This was inversely proportional. but that the velocities behave differently. And I don't know if I showed the velocity. I do. The velocities are different though, so I could have put another equal sign here, say that's velocity of A over velocity of B, and so I expect you to know this because there is a problem dealing with Snell's law. And that's the end of the grace notes. I guess I have a grace note thing at the end. Now, Linda, it seemed like somebody maybe asked a question, but I was not looking at.
Yeah, someone would like to know if we will end up using all these formulas in the exam.
Probably not, because we only have that list that Linda and I shared with you. So those are the kinds of problems that I'm asking. But a lot of them you will use, and certainly, and in fact, maybe that's a good way for us to go through. So Linda, I'm going to, I guess I'm just going to, let's see, what do I do? I'm going to stop sharing my screen now, which means I probably give it back to you. Why don't you bring up that list again of the problem topics then, Linda, please?
Yep, already did.
Okay, and that means I have to change the channel so I can look at it. Hold on. Where is it? There it is. Okay, good. Thank you, Linda. Okay, so you see, well, dimensional analysis means there's a bunch of things that you really need to know and should know. And there were, so I'm just kind of going through this. And I showed you equations for projectile motion and density. So you're going to be using those. I showed you equations for Snell's law. I showed you equations for intensity. For wave motion, I told you, you want to make sure that you remember, and I don't know if I actually pointed it out, but it was somewhere there in the grace notes, but velocity is equal to the wavelength times the frequency. Force, F equals ma, and knowing how to do vectors is really important. There's the Doppler equation, and so that's an important one. The range equation is, we talked about that, and that really is kind of a fallout of other things. But I am going to ask you questions like we did in the in the videos, and also in the classroom lecture dealing with the range equation. Pressure was the force perpendicular per unit area. Conservation of energy, we talked about having kinetic energy, potential energy, and two forms of potential energy, gravitational and elastic. And let's see, and Newton's three laws of motion. So, I mean, I guess, and Linda, you've seen these tests before, but I'm struggling a little bit. You'll have to know a bunch of those equations to do this, I guess I'll say, and maybe not all of them, but many of them, and they're all there for you to use. So that's my answer. Linda, you want to add anything to that, or?
Yeah, the idea of the grace notes is to give you guys the equations so you don't have to memorize them. It's not saying this is exactly what you're going to need to do the test, but this is all the content that we've talked about so that you have all the tools available.
Okay, thank you. I think that was well said. Okay, and maybe, and I know Linda, you got about 10 minutes or so before you have to run off for your other appointments. So can we do a little? Wait, maybe there's something here. Somebody's saying, hold on. I think that question or comment had to do with unit conversions and things like that. I'm thinking about the dimensional analysis problem, and inside the problem, I tell you what you need to know to perform the problem. So it's not saying, oh, go look at this all up in a table. Now, one thing that you will have to do somewhat routinely, though, and you should know how to do this, is how to change from millimeters to kilometers to, micrometers and things like that. But apart from that, I'm going to tell you many of the things that we need to know in powers of 10. Okay, so why don't I turn this over to Linda, and she'll tell us how she wants to do this thing of figuring out which one of these things we might want to talk about. And I could look up a problem or make up a problem or something, and we could talk about some of these more than that. And Linda, I think you would have done a noble service if before you do have to leave us this evening, you've given us a little bit of a roadmap of which of these or in what order we're going to do these. So.
Someone would like to know if the recording of this session will be posted soon. I'm assuming it'll be posted sometime tomorrow.
Yeah, it actually depends on how busy I am during my office hours. If I'm not really busy during my office hours, then it might get posted tonight. But also I'm even getting a little thirsty right now, so probably the first thing I'm going to do is go get something to drink after this lecture is finished.
All right.
Actually, go ahead, Linda.
I can see all of the participants, so I'm just going to read through the list. You guys raise your hand, which is the bottom on the far right. It should have like a little person with their hand up. So raise your hand if you would like to talk about this topic. So first of all, dimensional analysis. Anyone interested in that? All right, I'm getting 4 for that. How about projectile motion and density? Okay, that would be 2. Oh, looks like 3. Then how about Snell's law? Okay, I'm seeing 4. Next is intensity. Okay, just 1. Then we have wave motion. Okay, that would be 5. Next is force and vectors. Okay, that looks like 3. Next is the Doppler effect. I'm getting 7 for that. How about the range equation and 13 microsecond rule? Okay, looks like 6 people there. Then pressure. All right, I'm getting 4. Conservation of energy. All right, 9 people. I think that's the winner so far. And how about Newton's 3 laws of motion? Okay, that looks like 5.
Okay. Now I really and let's see. Nicole, is your hand up for a question or just you're volunteering for you're responding to Linda's poll?
I was responding to Ms. Linda's poll.
Okay, that's good. Thank you then, Nicole.
You're welcome.
Okay,
You're welcome.
so how
So
okay,
I would
so
say your top 3 would be conservation of energy, and then the Doppler effect and range equation 13 microsecond rule.
okay, so and I think we probably would do some noble stuff if we did that. And why don't you give me one more, Linda, and just in case.
All right, the next one would be wave motion.
Okay, so I will try to do those, and Linda is going to be vanishing in a bit, so she'll just kind of, discreetly go away. She's already reminded you about, the extra session she's having and stuff like that, and she might even send you an email on that. I don't know, or maybe she already has. Okay, so conservation of energy was something we have. So I'm going to talk a little bit about conservation of energy then. And again, I'm not necessarily going to solve a problem with it, but who knows, we might. So I'm going to go to a blank whiteboard, and I'm going to just make up kind of a conceptual problem. Okay, so you should be seeing my whiteboard. Now, did I share that with you?
Yeah, we can see it.
All right, excellent. Now I'm going to make up a thing then where we have some conservation of energy stuff going on. All right. So suppose, and this is the little story that I'm making up, I actually have asked this question on a test. I am not asking you this question on a test, but that's a horrible line that I just drew, so I need to erase that. Okay, so here is the story then that we're going to do. I'm going to make a line. And so here is what is happening. You're at the top, you're on a hill here. And so you're like that. And then you're going to be going down the hill. Let's think about this as maybe being a sledding hill or something. So then you go down the hill and you hit the bottom of the hill. And then, everybody, even me, has been on sleds before. And so you get this going on. And then, just to make it a little bit more real, I'm going to make there being a safety stop here for the sleds. And the safety stop is going to look like this. And then what we're going to have is I need to think about how I'm going to draw this. I'm trying to draw a spring. So that spring cushions this and absorbs what's happening. So, and what we're going to assume is, and this isn't completely realistic, but it's actually not a bad assumption if it's really slick snow. So we're going to assume that there is no friction. Now there always is friction, but we're pretending that there's not. Okay, so you see, and now I'm making up some things. And so from the top of the hill to the bottom of the hill, this distance from here down to here, I'm going to say is 20 meters. So this is kind of a bit of a steep hill. So this is 20 meters high. So this is going to be 20 meters. And so up here at the top then, what you have is you have potential energy. And let's see, I'm going to write it this way. So at the top, I'm going to be able to say potential energy is equal to mgh. Because that's the equation that you have for potential energy. Now the h in this case is 20 meters, and let's suppose we have a 50 kilogram kid. So we got a 50 kilogram kid, 50 kilogram kid. And we know that the acceleration due to gravity is 9.8 meters per second. So we know that g is equal to 9.8, this is meters per second, squared actually, meters per second squared. Okay, and H is 20 meters. Okay, so that is good. So we have that. So you see the potential energy that is here is 20 times 50, and 20 times 50 is 1,000, and then this is 1,000 times 9.8, so this is 9800. So this is 9800. So up here we have 9800 joules of potential energy. That's at the top of this sled hill. But then let's suppose that you timidly went to the end, and I realize that usually you don't timidly go to the end. Usually you're running and you jump on your sled. But let's just suppose that this 50-kilogram kid, the father is gently taking his son or daughter over and just, kind of giving it the slightest little shove, so they start going down the hill. Now what happens is this potential energy starts changing to kinetic energy. And so we could say, well, how fast are they going at the bottom of the hill? Okay, well, how fast they're going, that involves kinetic energy. And so this is going to be at the bottom of the hill, the kinetic energy, EK, kinetic energy is equal to, and this is 1/2, and this is m times v squared, where v is how fast you're going. Okay, so at the bottom, that's what we have. So you see this 9800 joules of potential energy is being changed into kinetic energy, and we're eating 20 meters of it by the time we get to this bottom. And we're not having to account for friction or anything like that in this particular example. Okay, so we made it to the bottom, and we have that. So I could have asked you the question of how fast are you going? Now Linda has left us to go off to another commitment, and that's fine. But that means we don't have a calculator here, and I'm going to reach out and just ask Amber, are you with us?
Yeah, I'm here.
Are you packing a calculator?
Yeah.
Good. Okay. So she's packing a calculator. So she's going to pound things into her calculator in a bit for us. I appreciate that, Amber. And the rest of you should be doing likewise, or maybe using Excel or something, because on the test you would have to do this. Okay. So anyway, coming back to this whole thing then. Okay, so we have this much potential energy is being transferred into this. So let's just go ahead and do this. So I am going to use my writing tool. All right, so I'm going to say that 9800 is equal to, it's 1/2 the mass of the kid, and it really should be the mass of the kid and the sled, but to pretend the 50 kilograms is the mass of the kid and the sled. Okay, so 1/2 of 50 is 25, so this is 25. That takes care of the 1/2 the mass, and then this is v squared. Okay, so now what I'm going to do is I'm going to ask Amber, because this means that v squared is equal to, I'm dividing by 25, so take 9800 divided by 25, please, Amber, and tell us what number pops out of your calculator with that.
392.
Okay, so this is 392, and you could check the units, but the units are fine with this, and because this is going to be meters squared per second squared. But then what Amber has to do is she has to take the square root of this. Now this is going to be less than 20, because 20 times 20 would be 400, but it's going to be damn close to 20. So let's see what Amber gets when she takes the square root of this.
19.80.
Okay, and that of course makes sense because that's damn close to 20. And I was kind of estimating that, so it's 9.8. So if I ask the question of how fast is the person going at the bottom of the hill, they're going 19.8 meters per second, and that's really pretty fast for at least for a little kid in a sled. Okay, but now what happens? Well, we're still going along the icy terrain, so we're saying that there's still no friction. We're still saying that. And so you're going along there. And so there's nothing to retard your motion. So you're going at that constant velocity of 19.8 for a while. So this is all this kinetic energy that you're having that's going along, and nothing is eating into the kinetic energy because we don't have any, what do I want to call it? We don't have any friction. Okay. All right, so that is good to go. But then we hit this spring, and you see we hit this spring, and it's a pillowed spring, so no one gets hurt here. But they hit this, but this starts crushing into the spring. Now we need to know what the spring constant is, and I'm just going to make up a number. Let's just suppose that the spring constant K is equal to 15. And that's probably a pretty stout spring, but this is a stout spring. So the kid hits it, but then this kinetic energy is transformed into elastic potential energy. So it's shoving this spring in. So we want to know how far did the spring get shoved in. So the first question was, how fast are you going at the bottom of the hill? But then now we're asking, because what will happen is this kinetic energy it eventually will stop the sled. And so what will happen is that all that kinetic energy is turned into elastic potential energy by shoving this in. And we remember that the equation for elastic potential energy, EL, is this little subscript that was on these equations we looked at. So EL is 1/2 times K, and this is x squared, where x squared is, how far it's shoved in. Okay, well, so we had kinetic energy and we can remember that actually the kinetic energy was all of this, so it really was, that's how much kinetic energy we had going in. So this was 9,800. And then this is going to be 1/2 times 15. And actually that's probably a punier spring than we want, but we're just getting a number here. Okay, so 1/2 of 15 is 7.5. And then this is x squared. Okay, so Amber, again, I'm going to ask you to contribute, please, with your calculator. Okay, so what's going to happen here then is Amber's going to divide both sides by 7.5. So she's taking 9,800 and dividing it by 7.5, and that's going to be what we have for x squared. And then she's going to take the square root of that. So Amber, let's do it one step at a time. So what did you get for x squared?
1,306.6.
Okay, very good. And now Amber's going to use her calculator to take the square root of that, and she's going to get a number. We'll just let her tell us what the number is.
36.15.
Okay, so you see this would compress this spring, and I probably picked that number to be too puny, but this would be 36 point whatever Amber said, and I'm just going to say 36 plus is equal to X. Now, okay, so the reason I did this was to show you that this is what conservation of energy is about. The energy has to go somewhere, okay? And this talked about potential energy being changed into kinetic energy. This talked about kinetic energy being changed into elastic potential energy. So we have all of that. Monica has a question for us. Go ahead, Monica.
Yeah. So what kind of question would be asked for this part that you just explained?
Well, the question that I just did,
Uh-huh.
maybe with different numbers, is a question I had on the final exam.
Right, but what would the question say for like this part that you just did with the
Oh,
left?
okay. Well, yeah. Okay. So what I would say is, first of all, I tell you a little story. I said, "Oh, you got this kid and his sled that has a mass of 50 kilograms, and they're just dropped off a hill that is 20 kilometers above the base, or 20 not kilometers, 20. That would be a long hill, 20 meters above the base. So, okay, how if the kid was just released at the top, then I could ask, how fast is the kid going when he hits the base of the hill? And that was the velocity part. And then I could say, but along the way, and this is more words, I would say, along the way, there is a spring that will, save the kids from getting hurt. And so they mash into this spring that's got a pillow on it, but it pushes the spring in. And I made up the spring constant there. So then I would say part B would be, how far does this push the spring in? Does that help, Monica?
Yes, thank you.
Okay, good. Any other questions on this one? Let's see. Yuyen asking, let's see, would the skier, I didn't see, Amber, can you say that in words, I think?
The skier LSA that you assigned, would that help with the first part of a problem like this? I'm guessing.
Probably so, yes.
Okay. Thank you.
Ewan, you have your hand up too. Oh, wait, Amber, I didn't mean to cut you off. Were you done or no?
Yeah, I'm done.
Okay, Ewan.
Yeah, I have a question. So, for the potential energy on top, and when they went down and got to the spring, so 3 of the 4 is equally, like when they went down, the potential energy is equal with.
Is converted to kinetic energy, yes.
Oh, okay. Yeah, I got it. Thank you.
Okay. All right, very good. Now, Linda gave us a whole bunch of things to do. We only have 2 minutes. And so what I'm going to do is I'm going to totally erase this, and I am going to do something that several people ask about, and that is the range equation, okay? And so I'm going to talk about this real quickly okay, and I guess I will use this little trash can thing to erase the board completely. Okay. We are doing ultrasound for the most part. And so that means when you're doing an ultrasound study, you have a transducer against a surface, but what you're going through is soft tissue. So the speed of sound in soft tissue is 1,540 meters per second. Okay, now, and so what this question deals with, the range equation, and you might want to go back and look at the videos that I did or things like that, but the range equation that we talked about before talks about the, why is it not working? I don't know. Talks about the go return time, because you see, this is what happens with your transducer. Your transducer sends a pulse, and then it listens for the pulse to come back. Okay, so the go return time, then is something. Now this, and I realize I have just a short amount of time, so I'm abbreviating this, but what we talked about was distance is equal to rate times time, or velocity times time. I guess that could be a v or an r, but distance is equal to velocity times the time, but the speed was 1540. So anyway, this is what the range equation says, or what the 13 microsecond rule says. For every 13 microseconds, and on the test, I probably would use a mu, but I can't draw a mu easily here. I can do it, but it would not be pretty. So every 13 microseconds of go return time, the depth of the reflector is 1 centimeter. So you see there's a host of things, and it's really important for students to remember, and I emphasized this when we went over it the first time, and so when you review that, you'll see that again, but it's really important that you understand go return times means goes down and come back up. And I don't remember the question that I asked, but I could ask how deep is it? And so that's a different answer than if you say, what's the go return time? But anyway, there's a problem dealing with this range equation and the 13 microsecond rule. Okay, I've enjoyed studying with you. I will have office hours later tonight. And Yu Yen, I think you're staying to talk to me for a minute. But first thing I'm going to do is I'm stopping the recording, and I'm wish you guys to be safe. Take care, and stay tuned for more about the upcoming test. I'm stopping the recording.